So today I'm going to be talking about some of the work that's been going on campus on large-scale sensing and control. So in specific, this project called Sensor Andrew. And one thing to point out here is that I'm one of many different faculty. So this list of names is all faculty working on the project across a whole bunch of different departments. So Sensor Andrew is essentially based in Senseer, which is a lab that works on sensed critical infrastructures. But we have people from civil engineering that work on application aspects of it, people from Scilab that are working on security aspects of it. So it's really a sort of interdisciplinary collaborative project. So hello. You've got to love it when that happens. I see. Maybe that's a lesson not to install Mountain Lion on your computer. Anyway, so to start off, I'd like to motivate sort of the work on Sensor Andrew by talking about some of the buzz that we've been seeing around Internet of Things. So on this slide, I'm showing a couple different projects that come from industry. For example, SenseWeb was a Microsoft project over the past couple of years where they're looking at taking devices and connecting them to the web and sort of displaying information to people. There have been other sort of private and corporate examples like PatJube and Cosm have been startup companies built around this idea. And then even some of the national labs like Sensorpedia is an effort by Oak Ridge National Lab to look into this problem of connecting devices in the world with different sets of users. So more recently, many of those projects kind of date back 5 years ago. More recently, there's been some of these projects that have reached really the sort of general public's eye. So for those of you that aren't familiar with Kickstarter, Kickstarter is essentially a public website where people can post ideas for projects, and then the crowdsourcing mentality kicks in and people vote on which projects they'd like to see succeed, and they sort of put in some of their own money to try to promote the projects. There was one recently, last year, called Twine, which actually came out of the MIT Media Lab, where the idea was to create this internet-connected, what looks like a soap block. But the idea was that it's a Wi-Fi-enabled widget that you could buy for your home. You could plug into sort of different things in your house, like you could put it on your washer or dryer, you could connect it to your front door. And these guys created a really simple rule engine for reading that data and turning it into tweets, emails, SMS message type things. And so these guys were asking for around $35,000 originally from Kickstarter. They ended up raising over $500,000, which at the time was the biggest and most successful Kickstarter project. So what you see from this is that sort of the general public is now starting to get into the idea of these internet-connected devices, and that maybe we're getting to the point where hardware is becoming cheap enough and there's a high enough level of acceptability that you'll really see these applications taking off. Since then, there have been a couple other projects. So Android at Home is kind of Google's effort in Internet of Things and connecting devices in the environment to users in their space. You've seen projects like the Nest thermostat, which have been in the news, which is a programmable thermostat that's internet connected. It talks to your smartphone. They also are filing patents on communicating with other devices in the home. So they essentially want to talk to motion detectors, lighting systems, things like that. And then the last sort of Internet of Things Kickstarter project was this Pebble Watch. So it's essentially a watch that's internet connected that can show you information from different online sources, which raised over $10 million. So it kind of blew the original $500,000 project out of the water. So what are some of the challenges in these Internet of Things systems, these sensing and actuation systems? Well, the first challenge that we faced when we started this project 2 or 3 years ago was describing the transducer data. So how do you actually put it in a machine-readable form that other systems can digest? You also, of course, have problems with scalability and extensibility. You've got a massive amount of data, which is potentially coming from thousands or millions of different sources. Each source could be producing a bunch of different types of feeds. So you come up with issues of which data do you keep? How do you actually want to process the data? Where does the processing happen? Does this happen at the edge? Does it happen at the cloud? So these are kind of some of the issues that we've been tackling in the Sensor Andrew project here at CMU. You, of course, also have lots of security and privacy issues associated with this. Issues of access control, making sure that you don't have covert side channels that leak information, You don't necessarily want everybody to know when your office light is on or off, because then they know when you're in your office. So lots of those types of issues. And then, of course, we have more system challenges about the fact that these are heterogeneous devices. A lot of the sensor nodes that are deployed at endpoints in systems are resource constrained. And a lot of the applications that you would develop for these types of systems, once you get to the really serious applications like heating, cooling, and control systems, are very application specific and domain specific. So you need to provide the right set of tools for people to be able to process and digest this information for their specific application use cases. So the Sensor Andrew project on campus is essentially our version of a software infrastructure which allows you to connect sort of legacy systems, different existing controllers, different sensors through an internet-based system to analytic engines, visualization tools, and different sort of processing resources on the back end. And so we've been looking at sort of accessing data, storage, how to deal with actuation, how to deal with latencies in these types of systems, describing the sensors, searching for sensors, at the same time maintaining security and privacy. So this gives you kind of a high-level view of Sensor Andrew and the different components that are involved. And as I said, many of these components are essentially individual research projects that are focused on by different faculty groups. So on one side, you have sort of different sensor networking protocols. So for example, my group works on 802.15.4 communication, so very energy-constrained wireless sensing devices that form mesh networks and push data back to gateways. We have other groups that are working on essentially cell phone type interfaces to connect to Sensor Andrew. We have a couple of groups who are working on security and access control in the system. So how do you actually provide the right hooks to users to control who has access to which data feeds? And so a bunch of these different avenues that are going along. Most importantly, we have a base of a bunch of different projects which are being supported by Sensor Andrew. So in this example, we have a picture of a smart home. So we have a group that's working on outfitting sensors and actuators in buildings to essentially save energy. There's a project called Body Track in the Robotics Institute, which is using the Sensor Andrew software to essentially track different medical and vital signs which they collect about people. And the idea is they look for trends in that data to try to detect allergies and pinpoint if people are sort of getting sick over time. We've got projects related to environmental monitoring, so water quality metering. We have a couple of projects working with industry on people tracking, so imagine in hazardous work zones. So a wide variety of these different topics, and yet we want to have sort of the same uniform background which they can all build off of. The most sort of exciting project right now on campus with respect to Sensor Andrew has been working with campus facilities. Because what they've been able to do is give us access to a whole bunch of legacy sensor feeds on campus. So every building that you go into will typically have a couple of different temperature sensors in each room, have a bunch of different motion sensors, and a lot of times they'll communicate on a proprietary backend to some heating and cooling system. So by working with campus facilities, we've been able to create adapters for these systems to pull that information into our Sensor Andrew infrastructure. And so we've been able to very quickly get tens of thousands of sensing points across campus. And so the idea there is that we're trying to help them build a uniform interface where they can actually really ascertain what's going on in campus. Right now they have a bunch of sort of discrete systems that don't work well together. So this is a high-level picture of the Sensor Andrew physical architecture. So what I'm going to do is go through each of the different 3 layers that we have and talk about some of the research efforts at each of the layers. So at the bottom, you essentially see a transducer layer, where we have a bunch of devices which communicate with each other. So there we're working on things like wireless sensor networks and different types of sensing technologies. We then have a gateway layer, which is essentially the glue that connects the sensing endpoints to the cloud infrastructure that sits on top of it. And I'll talk a little bit about some of the interesting challenges that come up at that layer. And then finally at the top layer, we have sort of our internet middleware, which allows people to write applications and develop for these types of systems. So down at the device layer, we have a few students now that are working on low power mesh networking. So we have a platform which we've developed at CMU called the Firefly Wireless Sensor Networking Platform. And the idea is to have a bunch of these devices which can be battery operated and can communicate data multiple hops back to a gateway. So this is not only just for sensing, but we've also looked at putting in quality of service properties to make sure that you can actually also do control over these types of networks. So we've looked at different control strategies. We've also, of course, looked at security within these networks. So how do you set up keys? How do you actually ensure data integrity? Those type of issues. If you drill down into some of the different sensing devices that we've created, we focus largely on environmental sensing, so understanding context in buildings and looking at how heating and cooling systems respond. Then we also have a whole bunch of work on different types of energy sensors, which kind of ties into a bunch of the efforts on campus around the smart grid and kind of the new energy center, which is being built and developed. This is just a picture of a kit which we actually deployed recently at one of the, or both of the national conventions, working with a particular government agency. So next I want to talk about what's happening at our gateway layer, so the layer above the transducers. So here, the real main issue has been around large-scale data manipulation. And to kind of highlight those challenges, I like to bring up the example of Google Maps. So Google Maps is one of these systems where you have very quick access from a web browser to an immense amount of information, right? You can essentially zoom in on any portion of this data and get richer and richer images. So the question is, well, how do they do that? Well, the answer is you usually use multi-resolution data access. So each one of these tiles kind of gets broken up and can get farmed out to a different individual server to handle the requests. Well, if you think about time series data, we have a similar challenge. If you're trying to access large amounts of time series data, you have this same scaling that happens as you zoom in, right? As you zoom in deeper and deeper into the data, you should be able to pull higher and higher fidelity information. In the case of Google Maps, the maps are tiled from a server at a data center, right? So they can essentially have full control over how they partition the data, where they store it, how they do replicas. In the case of sensor data and sensor networks in general, the data sources themselves are very much distributed. So the idea is the tiles need to be collected from field devices. These devices are typically resource constrained. They're embedded platforms. The devices are also bandwidth constrained, so you need to think about compressing information as you transmit these tiles. And then you also want to essentially hide latency from the system. So you need to think about things like caching and prefetching data that's of interest. So along these lines, we've developed a database / data collection system called Respawn, and the idea is that it's a distributed multi-resolution storage system. So we do some compression, data aging, automatic data migration, and intelligent prefetching. And so really the high-level goal is to provide APIs to users that can access data and seamlessly transition between a server backend and sort of the end node devices. So maybe the best way to explain this, since I see Greg walking in, is I'd like to show an example of the Sensor Andrew portal, and I can actually show how some of these components work together. So this is our main login interface where people would actually create and register a Sensor Andrew device. So if I log in, I see a list of different devices that my particular user account has access to. And I can see any device that has been created by me in this view. If I go to, for example, browse devices, assuming the network is going to cooperate, I get essentially what looks like a Google Maps view of the campus. And I have a couple of different buildings which are highlighted, and then I have different filtering properties which can search and bring up different transducers that are on campus. So if I, for example, click on one of these buildings, like Hammerschlag Hall, now I drop into what we call an elevator view. So now you're actually able to sort of hierarchically go through mapping systems and get down to the level of building floor plans. So here, for example, you see a floor map, and we see a couple of these nodes, which happen to be placed inside my lab. And so any device that's added to the Sensor Andrew system that's made open and public can be seen by any user that connects. But any device that I have access control over, that I essentially make private from other users, that only is seen by people with the correct credentials. So this is essentially the view of my devices plus any public devices. So if I click on one of these sensor feeds, it'll essentially give me the unique ID for that particular sensor, and I can bring up more details about it. So I can see what type of transducer properties it has. I get a QR code which will link a mobile device into that sensor. So you could print out this QR code and place it next to the physical sensor itself for people that are doing maintenance checks. Here, if I click on View History, what this is doing now is it's bringing up a historical plot of the data feed that we have in the system. And what you'll notice is as I zoom in to a particular point, it's going to start prefetching and sort of upsampling the data. So at a certain point, this data is actually stored on the server side, but once I zoom in far enough, you'll actually see a little bit of a delay where the system will automatically hand off to an edge point router. So the idea is that this Java application, which is displaying this data, is essentially calling some of our APIs, which allow you to rapidly access this vast amount of data, which could be distributed across different server points. And you can see that if you scroll, it's fighting me with the screen resolution, but if you scroll left and right inside this data feed, it should be, prefetching the edges of the data. So you can see that it's actually quite fast and sort of interactive. So that gives you kind of an idea of where we are on the interface side of Sensor Andrew. So this is talking about some of this prefetching which was happening, which is why the data was able to essentially get rendered so quickly. I see that I'm running out of time, so I'll talk a little bit about the high-level architecture. So it's a publish-subscribe architecture where every device in the system essentially has a unique identification code, which we call an event node. It looks very much like an email address, and essentially different agents can subscribe to those data feeds, and then devices which are producing information can publish data to them. And we, of course, have our domain data handler, which handles all of the warehousing and meta information backend that you could kind of see through the web interface demo that I showed. This system is also highly scalable, so we can do server-to-server federation, so you can have different domains of access control. You could have a server, for example, at CMU's main campus. You could have one at the Silicon Valley campus. And assuming those share credentials with each other, then you can share permissions and access controls for transducer devices across those domains. So I showed you guys already the web portal. We also have a mobile phone application which we're working on, which is allowing us to essentially tap into the student body for a lot of pervasive sensing. So we can have mobile sensing inputs which populate our data feeds. More recently, we've been looking at delay-tolerant data collection. So if you have devices that are actually out in the field that need to be picked up by data carriers that are driving by. So for example, our water monitoring project is heavily relying on the Postal Service and Verizon to actually collect data for us. And there's, of course, issues with making sure that data isn't tampered with, making sure that it's delivered reliably, and that we have end-to-end server acknowledgements with the data feeds. So last, since I'm running over time now, future directions. We want to build more applications. We essentially want this to become sort of an open source, publicly accessible system, at least within CMU. So within CMU, we already have a couple of groups that are using it. But eventually, we would like to open this up to outside of CMU. We're also working with groups at Google on data visualization, so how you actually manipulate and deal with these large data sets. And then with some of our work with Intel research, we're looking at cloud-to-edge partitioning and also building out our analytic toolkits behind the system. So thank you